Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Vector Integration from paper Mathematical Tools for Materials. Let's see what we are going to learn in this module. In this module, the topic of vector integration is taken up. First, the ordinary integration of a vector is described. Next, the central concept of line integral is introduced. Evaluation of line integrals is described by taking up examples. The special case of line integral of conservative fields is described in details with examples. Next, surface integral of vectors is described both for the case of open and closed surface. Evaluation of volume integral is explained by an example. Lastly, certain fundamental theorems regarding the line, volume and the surface integrals are described. The Gaussian theorem, Green's theorem in a plane and the Stokes theorems are indicated and proved. Some other fundamental theorems are also stated without proof. So now let us see the ordinary integration of vectors. After having studied differentiation of vectors and vector fields, our next task is to study the vector integration. The most useful concept in this regard are the line, surface and volume integrals of a vector fields. We first define the ordinary derivative of a vector quantity. If f is the vector function of a single scalar variable u, its integral over u is defined like the integral of a function of one variable. Let fu equals to I cap fx plus j cap fy plus k cap fz, then integral of fu du is equals to I cap integral of fx u du plus j cap integral of fy u du plus k cap integral of fz u du is the indefined integral of fu. If there exists a vector gu such that fu equals to d gu divided by du, then integral f u du is equals to integral d gu divided by du into du equals to gu plus k, where k is a constant vector. The definite integral between limits u is equals to a and u equals to b is integral from a to b fu du is equals to g b minus g a. The geometrical interpretation of this definite integral follows from an ordinary integral, namely, its three components are the areas of the curves of three components of vector fu. We now look on the integrals of a special interest to us, like the line, surface and volume integrals of vector fields and also of scalar and tensor fields. The line, surface and volume integrals refer to integral of a field over a curve, a surface or a volume in three-dimensional space. Let us see the line integral. A line integral of a vector field f is an integral of the form integral from a to b f vector dot dr. Very often the notation dl is also used instead of dr. The integral is to be carried from point in a space with position vector a to one with the position vector b along a designated path p. In case the point a and b are the same, that is, if we traverse a closed path in space, the line integral is usually denoted by a circle around the integral sign, like close integral f dot dr. To evaluate the line integral over an open or closed curve P, we define the scalar product of f with the displacement vector dl, which is a vector along the tangent to the curve at each point. Remember that in general the line integral over a closed path is not zero. For example, work done by a force, that is line integral f vector dot dr vector, may not vanish over a closed path. The most familiar everyday example is that of friction. Those special forces for which the line integral over a closed path is indeed zero are known as conservative forces. Evaluation of line integral. In Cartesian coordinates, let the points along the curve be designated by r is equals to x u I cap plus y u j cap plus z u k cap. Here u is a scalar parameter. Then f dot dl is equals to fx dx plus fy dy plus fz dz, and an integral from a p to b f dot dl is equals to integral from p1 u1 to p2 u2 into fx dx plus fy dy plus fz dz. Let us see some examples. So in first example, we have given an example of a curve in a plane. Evaluate the line integral of the function f is equals to y square I cap plus 2y x plus 1 j cap over the two paths as shown in the figure. Along the path 1, x is equals to y and dx equals to dy, and f dot dr equals to x square dx plus 2x into x plus 1 dx equals to 3x square plus 2x into dx. This implies that integral from 0 to 1 3x square plus 2x into dx is equals to 2. So for second path, in the first part dy is equals to 0, in the second dx equals to 0. So integral from f dot dr equals to integral from 0 to 1 x square dx plus integral 0 to 1 4y dy equals to 8 by 3. Let us see example number 2, where we have to find the total work done in moving a particle in a force field given by F is equals to xy I cap plus z j cap minus 10 xy k cap along a path whose parametric equation is given by x equals to 1 plus t square, y is equals to 2t square, and z is equals to t cube, from t is equals to 0 to t equals to 1. So integral f dot dr is equals to integral xy I cap plus z j cap minus 10 xy k cap into dx I cap plus dy j cap plus dz k cap, and integral from xy dx plus z dy minus 10 xy dz is equals to integral from 0 to 1 whole into 1 plus t square 8 t cube dt plus 4 t4 dt minus 6 1 plus t square t4 dt equals to 1726 divided by 105. Now let us study about the conservative fields. In analogy with the force, any vector field whose line integral is independent of the chosen path and depends only on the two endpoints is called a conservative field. Both the above examples are of non-conservative fields. In fact, there is a simple and well-known criteria to decide whether a given field is conservative or not. The result is given by following theorems. Theorem 1. The line integral of the gradient of a scalar function v xyz along any curve from point r0 to point r is independent of the path taken and equals to the difference between the values of function at the 2 points. That is, integral from r0 p to r del v dot dr equals to vr minus vr0, which is independent of the path chosen. Proof by definition. Dr dot del v is equals to dv, which implies that integral from r0 p to r del v dot dr is equals to integral from r0 p to r dv, which is further equals to vr minus V R naught. Theorem 2. This is the converse of the above theorem. If the line integral of a vector function about every closed curve vanishes, then it can be written as the gradient of some scalar function. So its proof: given that integral f dot dr equals to 0, let a be a fixed point in space and r a variable point. Draw any two paths C and C dash between these 2 points. Then C and minus C dash together form a closed curve, and hence integral a c to r f dot dr plus integral a minus c dash to r f dot dr equals to 0. This implies that integral ac to r f dot dr equals to integral from a c dash to r f dot dr equals to integral from a to r f dot dr equals to phi r. Since the integral is independent of the path of integration and depends only on the end point, let the 2 points be chosen infinitely close to each other. Then f dot dr equals to d phi equals to del phi dot dr. F is equals to del phi, or del cross f is equals to 0. Thus we have a simple criteria. Theorem 3. The line integral of a vector field over a closed curve is 0 if and only if the field is curl free. For example, f is equals to 2xy plus yz into I cap plus x square plus z plus xz into j cap plus y plus xy into k cap, then del cross f is equals to 0, that is integral f dot dr is equals to 0 from the theorem proved above. Now let us study the surface integral. Let S be two-sided surface. If the surface is closed surface, the outer surface is taken as the positive and the direction of the outward drawn normal is taken as positive. If the surface is an open one, then any side is arbitrarily taken as positive. Given such a surface and an element of this surface ds, we can associate with it a vector ds that is equals to n cap ds with magnitude ds and the direction given by n cap. Surface integral f dot ds is equals to surface integral f dot n cap ds as example of a surface integral. This is called the flux of f over ds. Similarly, we have surface integral f cross ds is equals to surface integral f cross n cap ds, surface integral phi ds, and surface integral phi n cap ds is equals to surface integral phi ds. Thus, mod of ds n cap dot k cap is equals to dx dot dy, which implies that ds is equals to dx dy divided by mod of n cap dot k cap, which implies that surface integral s f dot ds is equals to surface integral s f dot n cap ds is equals to surface integral r f dot n cap into dx dy divided by mod of n cap k cap, where r being the projection of s on the xy plane. So let us see some example. Surface integral f dot ds is equals to surface integral f dot n cap ds, where f is equals to z I cap plus x k cap plus 3y k cap over parts of the surface 2x plus 2y plus z equals to 8 in the first octant. So del of 3x plus 2y plus z is equals to 2I cap plus 2j cap plus k cap, which implies that n cap is equals to 2I cap plus 2j cap plus k cap divided by mod of 2I cap plus 2j cap plus k cap is equals to 2I cap plus 2j cap plus k cap divided by 3, which implies that n cap dot k cap is equals to 1 divided by 3. So f dot n cap is equals to z I cap plus x k cap plus 3y k cap into 2I cap plus 2j cap plus k cap divided by 3 equals to 2z plus 2x plus 3y divided by 3 equals to 16 minus 2x minus y divided by 3. For the projected surface in the xy plane, 0 less than equals to x less than equals to 4 and 0 less than equals to y less than equals to 4 minus x. Hence, surface integral S f dot ds is equals to surface integral r f dot n cap into dx dy divided by n cap dot k cap equals to integral from 0 to 4 dx into integral from 0 to 4 minus x dy into 16 minus 2x minus y, which is equals to 320 by 3. If the integration is over a closed surface, it is usually denoted by double integral with a closed loop. In general, we would expect the surface integral over a surface to depend on the boundary as well as the actual surface with that boundary. However, there is a class of functions for which the integral depends only on the boundary and not the actual surface. For such functions, the integral over a closed surface is 0. Evaluation of surface integrals is usually simplified by considering the projection of a given surface over one of the coordinate planes. Normal to the xy plane is k cap. The projection of a surface element ds with normal n cap on xy plane is given by volume integrals. Consider a closed surface in space enclosing a volume V. Then volume integral is an expression of the form volume integral phi r dv or volume integral f r dv. If phi is the charge density, then volume integral phi r dv is the total charge contained. For example, volume integral of the scalar function phi is equals to x square yz over the volume of the prism, which is shown. In this case, the integration can be performed in any order, so we write volume integral phi r dv is equals to volume integral x square yz dv, which is equals to integral from 0 to 1 x square dx into integral 0 to 1 minus xy dy into integral 0 to 2 z dz equals to 2 into integral 0 to 1 x square into 1 minus x whole square divided by 2 dx, which is equals to 1 divided by 30. The result can be interpreted as follows, that is df is equals to d of fx by dx into dx is the infinitesimal change in f as we go from point x to x plus dx. If the interval from a to b is subdivided into finitesimal parts, the total change in the function is the sum of the changes in each step, so that at the end it is equal the value of the function at the end point minus its value at the initial point. In other words, the integral over a boundary is related to value at the points. There are similar theorems for vector calculus as well as one each of gradient, divergence and the curl. If we move from a point A to point B along a certain path, then the change in the function over an infinitesimal interval dr will be fundamental theorems of vector calculus. Fundamental theorems of vector calculus is integral from a to b d fx divided by dx into dx equals to fb minus fa. So given a scalar f change in it over an infinitesimal interval dr will be d phi equals to del phi by del x into dx plus del phi by del y into dy plus del phi by del z into dz equals to del phi dot dr. The total change in the function will be integral from ap to b into del phi dot dr equals to phi b minus phi a, which is the fundamental theorem for gradients. Fundamental theorem for divergence. This theorem is also known as Gauss theorem. That is, volume integral del dot v dv equals to surface integral s f dot ds. This theorem is also known as Gauss theorem and sometimes as Green theorem. The boundary of a curve is its endpoints, that of an open surface is its perimeter, and that of volume is the enclosing surface. This theorem is also in the spirit of the fundamental theorem of calculus. In it, it relates the integral of the derivative of a function over a volume to the function at its boundary, that is, bounding the surface. Let S be a convex closed surface. Any line parallel to one of the axes will cut the surface in at most 2 points. In the case of line being parallel to the z-axis, such points will divide the surface into two parts, the lower and the upper part. Let the equations of the upper and the lower parts be respectively z equals to f1 xy and z equals to f2 xy. Let the projection of the surface on the xy plane be r. Consider first the z components of the vector f. For this component, we have volume integral del f3 by del z dv equals to volume integral of del f3 by del z into dx dy dz equals to surface integral r dx dy into integral f2 xy to f1 xy del f3 by del z dz equals to surface integral over r f3 xy f1 minus f3 xy f2 whole into dx dy. For the upper portion of the surface, dx dy equals to cos alpha 1 ds1 equals to k cap dot n cap ds1. Similarly, for the lower portion, dx dy equals to cos alpha 2 ds2 equals to minus k cap dot n cap ds2, which implies that surface integral over region R f3 x y f1 equals to surface integral over s1 f3 k cap dot n cap ds1. Similarly, surface integral over region R of f3 x y f2 equals to minus of surface integral over s2 of f3 k cap dot n cap ds1. Surface integral over R f3 x y f1 minus f3 x y f2 into dx dy equals to surface integral over s1 f3 k cap dot n cap ds1 plus surface integral over s2 f3 k dot n cap ds1 equals to surface integral over s of f3 k cap dot n cap ds, which implies that volume integral over v of del f3 by del z into dv equals to surface integral over s of f3 k cap dot n cap ds. Similarly, on projecting the given surface on the other two coordinate planes and adding all the contributions together, we obtain volume integral v of del dot f in dv equals to surface integral over s f dot ds. Physical interpretation. The left-hand side of the equation is the total fluid emerging out of the volume. The right-hand side is the total fluid crossing the closed surface enveloping the volume. And the theorem simply expresses the obvious equality of the two expressions. So let us see one more example. Now, the theorem can be used to evaluate surface or volume integrals by converting one into the other. So, let us evaluate surface integral f dot n cap ds over the surface of the cube with edges 0 less than equals to x comma y comma z less than equals to 2. For the function f is equals to 4 xy I cap plus y z j cap plus xyz k cap using Gauss theorem. So volume integral del dot 4 xy I cap plus yz j cap plus xyz k cap whole into dv is equals to volume integral of 4y plus z plus xy whole into dv, which is further equals to volume integral 4y plus z plus xy whole into dx dy dz equals to line integral from 0 to 2 dx, line integral 0 to 2 dy and line integral 0 to 2 dz into 4y plus z plus xy whole equals to 48. Green's theorem in a plane. Green's theorem in the plane can be regarded as the special case of more general Stokes theorem, which we use to take up immediately after this. Given two differentiable functions m dependent on xy and n dependent on xy, a closed region in the xy plane R bounded by a simple curve C. So Green's theorem in a plane states that line integral over a closed loop C m dx plus n dy equals to surface integral R of del n by del x minus del m by del y whole into dx dy. So let us see the proof of this theorem. Let the equation of the part AEB of the closed curve be y equals to f1x and that of ADB y equals to f2x as shown in the figure. Then surface integral R del m by del y into dx dy equals to line integral from a to b into line integral from f1x to f2x of del m by del y into dy whole into dx equals to minus line integral from a to b m x comma f1 dx minus line integral from b to a m x comma f2 dx equals to minus line integral over the closed loop C m dx. Similarly, working with the parts EAD and EBD of the curve, line integral over the region C of n dy equals to surface integral R of del n by del x into dx dy. On adding the two, line integral over the closed loop C of m dx plus n dy equals to surface integral over the region R of del n by del x minus del m by del y whole into dx dy. Since the surface is an open surface, direction of the normal n cap is not defined, nor is the direction along which the curve C is to be traversed is defined. There is a flexibility in the definition of one of these. However, once the positive sense of them is defined, that of the other is fixed by the relation. The consistency of the Stokes theorem demands the right hand rule. If the fingers point along the direction of the line integral, then position of the thumb gives the direction of the normal to the surface. Now there are infinite number of surfaces which have been the given closed surface as its periphery. Stokes theorem states that the surface integral of del cross f vector dot n cap is the same for all such surfaces, since they are all equal to the line integral on the right hand side. Ordinarily, the flux integral depends on the surface over which it is evaluated, but for curl of a vector it is independent on the surface and depends only on the boundary at the surface. Thus, for the curl of a vector function, we have the result, the integral del cross f vector dot n cap ds depend only on the boundary of the surface, and the integral del cross f vector dot n cap ds over a closed surface vanishes since the boundary line shrinks to a point. Vector function, we have the result surface integral s of del cross f dot n cap ds depends only on the boundary of the surface, and the surface integral along the closed surface S del cross f dot n cap ds over a closed surface vanishes. Proof of Stokes theorem. We now come to the proof of Stokes theorem, which, as we have mentioned, can be regarded as the generalization of the above proved Green's theorem to the surfaces in 3 dimensions. So let S be the surface whose projection in the 3 coordinate planes are regions bounded by simple closed curves. The equation of the surface can be written in any of the 3 given forms, that is x is equals to f yz, y is equal to g xz, and z is equals to h xy. So now consider the first term. Surface integral is of del cross fx I cap whole dot product with n cap ds. Del cross fx I cap dot n cross ds is equals to del fx by del z into n cap dot j cap minus del fx by del y into n cap dot k cap whole into ds. R is equals to x I cap plus y j cap plus z k cap equals to x I cap plus y j cap plus h dependent on xy k cap, which implies that n cap dot del r by del y equals to n cap dot j cap plus del z by del y of n cap dot k cap is equals to 0. So this implies that n cap dot j cap is equals to minus del z by del y into n cap dot k cap, which implies that del fx by del z n cap dot j cap minus del fx by del y into n cap dot k cap is equals to minus del fx by del z into del z by del y into n cap dot k cap minus del fx by del y n cap dot k cap equals to minus of del fx by del z into del z by del y plus del fx by del y whole into n cap dot k cap. Or we can write del cross fx I cap whole into dot n cap ds is equals to minus of del fx by del z into del z by del y plus del fx by del y whole into n cap dot k cap ds. Now on the given surface S, fx dependent on xyz equals to fx dependent on xy h again dependent on xy equals to gxy. This implies that del fx by del z into del z by del y plus del fx by del y is equals to del g by del y. Hence, equation becomes del cross fx I cap dot n cap ds is equals to minus del g by del y n cap dot k cap ds, which is equals to minus del g by del y dx dy. Using this expression in the surface integral, we have surface integral s of del cross fx I cap whole dot product with n cap ds is equals to minus surface integral over r del g by del y into dx dy. Now we use the Green's theorem in the plane and obtain surface integral s of del cross fx I cap dot product with n cap ds is equals to minus of surface integral over r of del g by del y into dx dy is equals to line integral of closed loop c dash g dx, where c dash is the boundary of the planar region R. Since at each point xy of c dash the value of g is the same as the value of fx. At each point x, y, z of C. And since dx is the same for both the curves, it follows that line integral along the closed loop C dash of g dot dx is equals to line integral along the closed loop C of ax dx. This implies that surface integral S of del cross fx I cap dot n cap ds is equals to line integral of around closed loop C ax dx. On making similar projections on the other two planes and adding the results together, we get surface integral of del cross f dot n cap ds is equals to line integral along the closed loop C of f dot dr. So now let us see one example. F is equals to 4x minus y whole into I cap plus y square z cube j cap plus y cube z square k cap, where S is the upper surface of x square plus y square plus z square equals to 1. Boundary is the circle x square plus y square equals to 1. If the path is traversed along the counterclockwise direction, the normal to the surface will be upwards. So write the equation of the circle in the parametric form as x is equals to sin t, y is equals to minus cos t, 0 less than equals to t less than equals to 2 pi. This implies that line integral along the closed loop C f dot dr is equals to line integral from 0 to 2 pi of 4 sin t plus cos t whole into cos t dt is equals to pi. On the other hand, del cross f is equals to k cap, which implies that surface integral along S of del cross f dot n cap ds is equals to surface integral along S of k cap dot n cap ds equals to surface integral along region R dx dy equals to pi. Let us see some other important theorems also. Green's first identity, that is volume integral over V of phi del square xi plus del xi dot del phi whole into dV equals to surface integral over S of phi del xi whole dot product with ds. The second Green's theorem's identity, that is volume integral over V of phi del square xi minus xi del square phi whole into dV equals to surface integral over S of phi del xi minus xi del phi whole the dot product with ds. Another theorem is divergence-like theorem for curl, that is volume integral del cross f dV is equals to surface integral along the closed surface S ds cross f. Stokes-like theorem for scalars is line integral along the closed loop C of phi dr is equals to surface integral along S of ds cross del phi. So students, let us summarize what we have learnt in this module. In this module, we have taken up the topic of vector integration. We have first described the ordinary integration of a vector. Next, we have introduced the central concept of line integral and described the evaluation of line integrals by examples. Then we have discussed in detail the special case of line integral of conservative field and proved them on the condition for a field to be conservative. After that, line integral was described as surface integral of vectors both for the case of open and closed surfaces. Then we have explained evaluation of volume integral by an example. We have next stated and proved the very important fundamental theorem regarding the line, volume and surface integrals like the Gauss theorem, Green's theorems in a plane and the Stokes theorem. Finally, we have stated some other useful theorem without proofs. Thank you.